All right. I see it's 2:02 Friday afternoon, so I propose to make a start again. So this afternoon, Gilles, you will be talking about more like the availability of some heavy metals on the one hand and micronutrients on the other, and especially as well, I think, on the cation exchange capacity and the determination of the texture or the clay content. So give the floor to you. You can go in presenting mode. I'll check if I have a nice screen, and please go ahead.
Yeah. So yeah.
Is it possible to make the uppers? Yeah, okay, that's better. Thank you, Gilles.
Okay. So here is the second session of the day about, as you said, the soil micronutrient analysis and sizing the fridge in reference to the cationic exchange capacity viewed as a fridge for the subs. So regarding the micronutrient analysis, we followed the DTPA extraction, which is the SOP from the FAO. And after we'll discuss about the particle size distribution and the cationic exchange capacity. And then I will share some slide about the integration about the various data linked to the soil fertility. But it's a work still in progress, and that should be continued somehow, some when. So regarding the list of available SOPs, so we had from the FAO the trace elements by the DTP extraction and also the cationic exchange capacity. So we followed both. Regarding the SOPs from Ukraine, there was one about trace metals, but it's a collection of different SOP, one for every metal. Then there is a granulometry method by the pipette. Also, there is a SOP about exchangeable cation, which looks like the cationic exchange capacity, because in CEC there is also the determination of the exchangeable cation. And in southern Belgium, we use the Lacanet-Nervieux for the trace elements. We recently used the ISO method for the bisedimentation for the particle size distribution. Previously, we had a mix of various analysis. And there is also the cationic exchange capacity by the Cobalti examine that we use sometimes when we want CEC at the pH of the soil. So I put some slides also in about plant analysis in this part about micronutrient analysis, because that's the main focus we have on when we analyze plant. It's mostly in order to see the uptake of micronutrient or of contaminants. So I put two slides about the method that we use. I wasn't sure that it was seen elsewhere. So regarding the micronutrient in soils, here with this example of zinc in the soil plant system, again, the plant must take up the elements through the soil solution, and the part of the zinc that will be in the soil solution will depend on the interaction with the soil constituents. They can be complexation, sorption, and solubilization, dissolution, precipitation processes with the various solid phase of the soil. And usually there, for every metal, there exists a lot of extractant that have been tested. So the best fitting of the relationship between soil and plant depends on the element, depends on the plants, depends on the properties of the soil. So it's not so easy to have a universal relationship. However, searchers try to find the most appropriate, which is convenient for the biggest number of metals as possible. Regarding what exists and is often used, you have the CaCl2 0.01 molar, which is used and is referred as the soluble, instantaneous soluble content of metals. And then you have the exchangeable, which are forms that may not be used directly, but is susceptible to go into the soil solution through the reaction between the solid phase and the liquid phase. So it's considered as available for if you integrate the processes under a longer time than just the instantaneous moment. So as extractant of the exchangeable, you will find CH3CONH4, so ammonium acetate at pH 7. That's the extractant that is used for the cationic exchange capacity. And so you are going to take the easily exchangeable elements that are on the cationic exchange capacity. If you add EDTA and you go to pH more acidic, you will take this fraction plus carbonates that may be dissolved, and also weakly crystallized oxides, which will dissolve in the soil solution. The same with the DTPA extractant. You are going to take a fraction a little bit more, a little bit bigger than just the exchangeable. There are other extractants, but after, if you go to the aqua regia, you will have an approximation of the total, which is called the pseudo-total fractions. So it means that you don't dissolve the well-crystallized silicates. And if you use fluorhydric acid, so in the three-acid method, you will get the total forms. Also, alternative is to use non-chemical reactants, such as the XRF, for example. So there is a lot of protocols in the literature, and some are more used than others, but it's difficult to say that one chemical extractant will be appropriate for or relevant for every metals. Regarding the levels of micronutrient in soils, there's been a lot of work. I found a FAO report from the 80s, I think, where a lot of things were already done regarding the levels in the world, the needs of plants and so on. But again, difficulty is to compare between protocols that were not exactly the same everywhere. More recently, there was a study that was published by Moreno Jimenez et al. In the Global Change Biology, and they made a kind of modeling of the content of the micronutrients in the soils over the world, and comparing the lowest developed countries with the most developed countries. I say that in in continents like Africa, it was more difficult to have. They have lower contents of micronutrients, and there was all the parts of the world are not equal to face this issue. I found also range levels of micronutrients in soil. It's not so easy to the threshold where the plant needs additional fertilizers in these elements. Usually, there is more practice in looking at when there is problem, when there is symptoms of deficiencies in or excess in the morphology of the plant. You make analysis and you say, okay, you have a confirmation that levels are really low. The levels, the threshold that you should use are probably context dependent. Again, here it's can find some levels in Canadian soils. So in Alberta, they propose some. I try to use them at the end in order to assess the levels that we found here for the Ukrainian soils, but we don't have the guarantee that these results are really relevant. So they define the threshold between deficient, medium, and adequate level for boron, chlorine, copper, iron, manganese, and zinc, and it was with the DTPA extractable, so there is a base of comparison. Regarding the analysis, again, like previous one, it is determination, which is based on the contact, agitation, filtration, and then it is we use the ICP-OES, and we follow the SOP from the FAO. So principle, it's like I think it was for potassium that I presented it. There is acetate ammonium buffered in pH 4.8. So that's in the that's in the Ukrainian methods. They use acetate ammonium buffered at pH 4.8. So there is no EDTA or other kind of chelating molecules. So we will have a comparison later. Regarding the FAO-SOP, the methods is proposed as an indicator of plant available for a series of metals such as copper, iron, manganese, and zinc, which are the target micronutrients, but also for other elements such as the heavy metals. So this method should be applicable to all types of soils, but yeah, you cannot aim to have a perfect correlation with all plants and all types of soils, all crops, all varieties. So the principle is was developed by Lindsay Novell. It was mainly developed for near neutral and calcareous soils, where these elements are the more susceptible to be deficient because they are blocked by the acidity, the basicity level. So they are keen to precipitate at these pH, and so they are less available. And so the sample is extracted in a mixture of DTPA, TEA, and CaCl2 at temperature of 25 degrees. The extraction solution is buffered at pH 7.3. And so DTPA is chelating agent, so it means that it forms complex with the element that you want to measure. Yeah. The use of CaCl2 here is in order to minimize the dissolution of CaCO3 when you have calcareous soils. So regarding the procedure, first you have to weigh 10 grams of sample and in 20 milliliters of DTP extraction solution to shake for 2 hours and then to filter the extract, filter or centrifugation tubes. So as the ratio is a bit short, it's 1 to 2. For soils with a high organic content, it's possible that the organic matter absorbs the water and that there is not enough volume of extract. And so they propose to, in the norm, they propose to adapt. When you have your extracts, it must be analyzed within 48 hours. Yeah. Otherwise, I don't know exactly if you. Sometimes when you know that your extracts, it will last a little bit. You can acidify. You put a little bit of HNO3. That's what we do with the CaCl2 extract. I don't know if it's possible here for the DTPA. So here is the soil after centrifugation. Yeah, you see it's not completely clear, and then you filter, and at the end the solutions are clear. Sometimes you see that you have some samples which are very brown, very dark. Usually the flame, the equipment which work with flame don't like very much these kind of solution. So for the determination, it's like for the other elements, you should use single element standards or multiple element standards, depending on where you are, with what equipment you are working. With the ICP, usually we put standards of multiple element in the same flask. And of course, if you need to follow manufacturer's recommendation and to dilute the extract if you need to dilute. At the end, we have small samples like that in small tubes, and we go to the ICP OES where we can have the measurement here. It's real photos of the samples where we measured copper, iron, manganese, and zinc in the samples from Ukraine. So if we look at the results now, we compared the method that we used with the EDTA with the results of Ukraine, which were obtained. I don't know why is that one? No, yeah, sorry. We compared the results from Ukrainian methods with the DTPA extractions, which are the blue points, and with the EDTA extraction, which are the orange points. The line one is there. We see that with the DTPA, we are extracting more copper than what has been extracted by the Ukrainian methods, which is only ammonium acetate and has no DTPA. We know that for elements like copper, they have a relatively high affinity with some chelates, and so that's probably the chelating agent that have taken this copper more than for the Ukrainian method. And if you look at the EDTA, which has other chelating properties, you see that the levels of copper in the solutions are quite much higher than with the DTPA. So it means that regarding the elements that you will take into consideration, the chelating agent that you put in the mixture is really, really important. And so it means that the results of interpretation should be adapted to these differences of methods. If we look at the iron, the same, we see that we have not so good correlation. See that there are some very extreme points here which are giving an influence on the good, apparently good R square, but if you look at the other points here, they are a bit far from the lines. So we could say that for some of the points with the DTPA, you have a good relationship between DTPA and Ukrainian methods, but there are some soils here which are clearly extracting more with the DTPA. And for the EDTA, we have the same here. We see that we extract more than DTPA, and for the low levels of elements in soils, we have big differences. See that here it's 100, where it's less than 10 for the other methods. Manganese looks like the relationship is really lacking. The regression line are quite flat. We can see that the method with EDTA should dissolve more elements, more manganese oxides than the other one. So there is with this method probably a big contribution of these oxides and the elements that are sorbed on these oxides in the final solution. Yeah, and the extraction between the DTPA and the method, Ukrainian method, is clearly not well correlated. If we just look at here is the same graph but without the EDTA, we just focus on the relationship between DTPA and Ukrainian methods, and you see that clearly there are some points which have no relationship with each other, so they are barely comparable. And regarding zinc, we can see that there is a quite fair relationship between the DTPA and the Ukrainian method. The points are not so far from the 1-1 relationship. There is a bit more different for the EDTA, but looking at all the four elements, it seems that the zinc is the less different according to the three different methods. It's, to my opinion, clearly linked to the fact that it is less sensitive to chelation than the other one. So we try to have a look within the 39 samples of that we analyzed at their situation compared to the reference table that I showed for the soils of Alberta. If we have a look at the same threshold for Ukrainians, Ukrainian soils, the copper, see that they should be in classes which are middle and high, and so there should not be risks of deficiency for the copper. The same for iron. It's even the iron content is much higher than the levels that were found in Alberta. Manganese too. And regarding zinc, there might be a little bit 9/39, which should be classed as risk of deficiency. So I added 2 slides about the analysis of plants, because sometimes you can consider that you would have risks of deficiency or risk of accumulation. Our method is that we weigh 2 to 5 grams, depending on the quantity of materials that you have and what you expect as quantity. If you are measuring major nutrient, you don't need a lot of material. But if you know that it will be at very short concentrations in the plant, you try to use as much as possible of plant material. So 2 to 5 grams, usually dried at 65 degrees centigrade maximum, and then crushed into powder or cut in small pieces. Put in beakers. We add the mixture, 30 milliliters of the mixture of HNO3 and HClO4. We leave overnight, and then we put on a warming plate here, and in order to evaporate the liquid until it is dry. And then we dissolve the dry residue in 5 milliliters of HCl 10%. And when the residue is dissolved, we pour it in a 25 milliliter flask with the distilled water. We put it at a level, and then we filtrate on paper, and we measure by flame spectrometry. So I just put this to show, but of course, if you want to see a relationship between the element in the soil and the element in the plant, if you want to see linear relationship, you must be in the conditions of deficiency. It's more easier. Here we have, it's an example of measurement that we made in salads with we measured zinc content and copper content. You can see that there are absolutely no relationship between the both for the copper and maybe a small trend, but with very poor R square between soil zinc content and plant zinc content. But this relationship could be more valuable if we had less zinc in the soils. We maybe should see a trend of progress. Oh, okay. That was for the micronutrient. Maybe before going to particle size distribution, we can open the floor for question.
Yes, thank you, Gilles. I was wondering in the graphs that you showed between the relation of the EDTA and the DTPA, was it only the chelating agent that was different, or was there also a difference in pH and other extractions, or was it like the same extraction solution, or only the extractant?
Yeah, you're right. The extraction is higher too. The pH is at 7.2 for the DTPA. It's at 4.6 in for the EDTA. Yeah, it clearly must be responsible of something. Yeah.
Yeah, but it shows definitely that different extraction procedure
Yeah.
will lead to different results.
Yeah.
I was also looking to the quality control. Is there? I was checking now. Is there any like certified reference material, or in order to? I know these extractions are operationally defined, but is there a way how you can control as a laboratory if you perform the extraction well to some extent?
We have control samples. We have two kinds of control samples. We have BPA in France, for which we have reference values for a series of analytical elements. I think that we have reference values for the total content, quite sure. I'm not sure we have a reference value for DTPA or other, and or EDTA. The alternative is that as we are making our own proficiency test, we have control samples that we distribute among our network, and yeah, we make repetitions on this, and we know globally what levels, what is the variability. Yeah.
Mhm. And if you perform these interlaboratory tests with these kind of extraction, what is more or less the variability you can expect? Is it more than, for example, doing aqua regia, or is it the same order of magnitude in variability that you see in the results?
It's difficult. I don't have the answer right now, but in the proficiency test, we do it with aqua regia, and we do not make it for the trace metals. We do not make it with the acetate EDTA.
Okay.
We know, but yeah, we have in our own system we made a assessment of the repeatability of the methods, but I don't have the numbers. I could not answer to that question. I will try to note and to maybe give you later this information.
Okay, thank you, Gilles. No, I think most important is that indeed you show very well by doing these different extractions on these soils that the results may differ a lot. So indeed, you have to be very careful when doing interpretation. You need to check which method has been used, and also, as you did for comparison with reference values, also make sure that they use the same method, and even though maybe also the soil type can have an influence. So it's indeed something to be aware of. Thank you. And then I also received a question. Have you compared DTPA and EDTA solutions before? How different were they? So I think before this study, if you ever have some experience with that, Gilles.
No, probably. I think there are some papers which deal with that. I could find them, but no. For us, it was the first time we used the DTPA extraction. We had some comparison recently with other extractions such as HNO3, CaCl2, others like that, but we did not compare DTPA. But yeah, the idea is that when of course the more aggressive reagent you use, the more you dissolve the element. It's a bit obvious, but yeah.
Yeah. I just put in the chat, I found a reference to one of the methods comparing EDTA and DTA on a reference method but I don't know if it still exists. It's date back already from 97. So I just put it in the chat so that the people can have a look at it. I mean, this gives also comparable data between EDTA and DTPA, and maybe also a link to reference material if needed. Yeah. Okay, I hope this answered the question. All right, Gilles, I think I don't have any more questions on this topic, so I propose
another point I was thinking with this, it's clear that the EDTA method is a bit aggressive, and if you want to, for example, in research, if you want to make experiment and have a look at, you put amendment in your soil and you want to see the effect, so on. This kind of treatment is far too aggressive to monitor these kind of things. You must take a more smoother reagents such as CaCl2 and so on. This one we know it's aggressive, yeah. Okay.
Okay, thank you.
So we go to particle size distribution, and there might be two differences between the methods. Usually, it seems for me it was clear that when I was taught by my teachers that clay was all the particles below 2 microns, that between 2 and 50 microns you had the silt, and between 50 microns and 2 millimeters you had the sand. But looking at work of pedologists elsewhere, or work of sedimentologists, and work of physical engineer for the stability of the soils and so on, you see that it's not so obvious that the reference are well established. And so you must first define in which referential you will work. We here, and I think it's the protocol in the FAO too, we work with the USDA system with the different classes of size of particle. And I know in other systems, the limit between the clay and the silt is fixed at 1 micron. And I think it's the case for a Ukrainian soil, a Ukrainian system of classification. So the idea here is that in the soils, there is a structure into aggregates, can be macro or micro aggregates, but it's a assemblage or of the physical particle, the mineral particle, and cementation molecules in between, which give them a structure. And the idea of the particle size distribution determination is to have an idea of the distribution of the mineral constituents of the soil between the various size classes. We want to eliminate all the elements that could make cement, that could make a link between these particular elements. So if we take that, for example, it's an aggregate with different sizes of mineral particle. The binding agent in brown here could be organic matter. It can be cation, it can be oxide, depending on the place where you are. And the idea of the particle size distribution is to completely eliminate the cement between these particles and to class them according to their size. So I found a presentation from a Ukrainian researcher at a conference in ISPRA. And so in the presentation, it's clear that the size classes that are used are not the same as the one we use there, and we saw it too in the results that we received from Ukrainian for the particle size distribution, and it might be difficult to compare the results. If we wonder why studying particle size distribution, at least we know that the soil functioning might be different according to the texture of the soil, and there are classification of soils of soil texture that group globally kind of similar functioning, and they are represented by this kind of texture triangle. Here it's in the USDA system, where you have the classes of clay, loam, silt, and the sand and the intermediate fraction. So it might be a way of evaluating globally the type of soil texture and an evaluation of the physical functioning, for example. And also other kind of analysis which are made if you differentiate more fractions than only clay, silt, and sand, but you are different kind of particle size. You can compare the soils. Here you have, for example, two soils which are completely different. It's the cumulative percentage of particles according to their size. And with different kind of curves, we can say that the soils will have different kind of functioning. And also, if you compare the various layers of the same soil, you can have an idea of the pedogenesis processes that help to put in place these soils, and see if all the horizons have the same genetic origin or not, for example. So there are many kind of textural triangle. Here it's the one which is used for the detailed soil map of Belgium. So the classes that are mapped on the Belgian map have a first letter which gives you an indication of the texture. U is for heavy clay and so on. Most soils are at A texture, which is typical of the loamy sand or the silty area. And I took these images from the description of our package that is dedicated to the plotting of your data on this kind of triangle. They made the package for many different kind of triangle from different countries, but I didn't find for Ukraine. So regarding the procedure, we followed ISO 11277, and I took some of the text here, some of the slides from a presentation that was made by Chris Banov for the GLOSOLAN. There was a thematic GLOSOLAN workshop about texture. I put the link here. If you will have the presentation, I invite you to, if you want to know more about this, to follow the link. And so globally, the principles are given here. The soil, we work on soil sample, air dried or at 40 degrees, and grind it at 2 millimeters. The idea of the method is sieving the soils and sedimentation of the smallest size particle. And for that, you first have to remove the binding agents, which are the organic fraction, the carbonates, and the soluble salts, if any. I put also reference to the sedimentometer methods, which is Bouyoukos. I will just show some images of it's an alternative method, but it's not very used in the publication. So the idea is that you make a wet sieving. So first you remove the binding agent, then you will make a wet sieving of the sand on one side and silt and clay on the other side, and you will measure the sand and clay by pipette method. And for that, we use a peptizing agent to help to disperse the particle as much as possible. And that's it. So on one side, after sieving at 50 micron on one side, we have the sand. And on the other side, we have a suspension that we put into a sedimentation column. And the principle of the measurement is that we will make an agitation of the solution and leave the particle settled down to the bottom of the column. And the idea is that the bigger particles are going to the bottom faster than the little one. So that's called the Stokes law. And so if you follow this law, you can guess according to the time, the dimension of the particles that will be at a given distance from the upper part of the column. So here, what we did. So first, it's of course the sediment, the weighing the soil particle. We use 2 millimeter soil, and we weigh 15 grams for the soils. And for the Bouyoukos, it needs more dense solution, and usually it is recommended to use 50 grams of soil. So the first step is to remove the organic matter, and you do it with the H2O2. In the procedure, you should add 100 milliliter of H2O2 in progressive steps, because according to the content of organic matter in the soil, I will show you some image of what you should not do. According to the levels of organic matter, you can have a strong reaction and a lot of foam that is made. So there is a reaction between H2O2 which will oxidize the organic matter. So the idea is you put your H2O2, you cover, and you leave it until the next day. So that's called the cold attack, and then you have a warming attack. And in the procedures, this is going to say to gradually increase the temperature to 70 degrees. And then after, you can increase temperature and during approximately 15 to 20 minutes. This is indicative because according to the soil, you may need to attack. The whole attack can last 1 hour, or it can last 2 or 3 or 4 days, because you have to repeat the the attacks again and again, because there is a lot of organic matter or a lot of attacks to make. So I don't know why there is this here. It should not be. So the idea here is that when you add some H2O2, you have the development here of a foam. You see, and the foam will develop. So this is at cold attack. Usually this comes after a warm attack, but sometimes you can have already this kind of foam formation during the cold attack. And when you see that, you know that you will have very, very long day of attacking the soil particle. So before we were using this kind of device, so they are a Bunsen back with the flame, and we put the beaker on the flame for the attack. You see that there are lots of reaction. You see that the beaker are very dirty, so it's not very good. And sometimes you are obliged to put them out of the fire. And with this system, an old system, you really don't have any control of the temperature. And often we had this kind of result. You see that with this one, you can wash it and do it again. And so I should not show you that, but that's the real life. Yeah. So now we work more soft attack, and the beakers are put in a water bath that is warmed here before being finished on a hot plate, and it is really much more convenient for everyone. Hopla. So that's the attack. After so when there is no development of foam anymore, you can consider that the attack of organic matter is finished, and you still need to remove the carbonate and the calcium link that you could have. And so we use HCl. So there are variations. We use 50 milliliters of 0.2 normal HCl. I know that others use 10 milliliters of one normal HCl. And boiling. If you have carbonate, you must put additional HCl. For every percent of carbonate content, you add some more milliliters of concentrated HCl. Then boiling, then let it cool down, and you put water to wash the excess of acidity, and you put it on the side with water, and you leave the sedimentation occur. And when the upper part of the liquid is completely clear, so not in this situation, when it's well clear, all the particles are settled down, and there are no colloid, you can suck the water and repeat the washing. So at the end, you control with the paper pH the pH of the suspension. So the idea is to remove the acidity and not going too far, because when the pH rises, the peptization begins to occur in the beaker, and you cannot remove the excess of water anymore. So when it's okay, you put the dispersion agent we use hexametaphosphate of sodium. And in our procedure, we boil 10 minutes and we leave it cool down, and then we agitate 2 hours. So there are a different kind of procedure. Then we have, after the 2 hours of agitation, we make a separation of wet sieving. So we have here a 50 micron mesh sieve, and we just pour the sample on it. Here you have a bottle, but usually we take directly the column of sedimentation. We wash the sand, and when the liquid is clear, we take the what is left on the sieve goes in a small beaker where it is the sand fraction. So we wash it. We wash this, and when liquid is completely clear, we put it in the beaker. So it will be here the beaker with the sand fraction. We put it in the oven, and then we just wait. And by weighing this quantity, report. We know how much sand there was in the sample. Then we have the columns of sedimentation. Here we put them in a water bath, and the idea is that you can control the temperature, because the Stoke law depends on the speed of the particle will depend on the temperature. The more high, the highest the temperature, the highest the speed of the particles. And so by selecting the temperature and selecting the deep of sampling, you can calculate the time that is needed to collect a particle according to its size. For example, if you want to measure the clay content, you must shake the solution at 30 degrees. You wait 6 hours, a little bit more than 6 hours, and you can make sampling at 10 centimeters. Or if you are more in a hurry, you can take the suspension at 5 centimeters, and you wait something like 3 hours. So there are different kind of possibilities. The idea is to try to do the same for every sample, same procedure. Globally, we work with the water bath at 30 degrees here, and we make 3 different measurements: one after 3 minutes, one after 13 minutes, and one after 3 hours, but at 5 centimeters. We made the sampling. So we have a first fraction which contains the particles which are have a size of less than 20 microns. The second sampling is less than 10 microns, and the third sampling is particle less than 2 microns. Yeah, so this is the the less. No, it's less than 20 here. I think I made an error. So first sampling less than 20, second less than 10, third less than 2. We collect with the pipette 25 milliliters that we pour into these small cups that go after at the oven at 105 degree, and we will weight these particles. Yeah, and so that's the place where we weight. We just animation of how we weight. This is just because I'm happy I discovered that we had a function of automatic transcription in the Excel file when you put on the button. So that's globally the idea. You have a different kind of sampling. You weight and then you make a calculation according to what you have put. You had 15 gram at the beginning. You must know how much water there is in your soil sample. You must know how much organic matter there is in your sample. You must know how many carbonates you have in your samples. All these, you remove them from the 15. So you know that you had, for example, 12 grams of solid mineral particles in the soil. You measured 5 grams of sand, so you have 5 grams divided by 12 and a half, and you have the percentage of sand. The same for the clay particles, and you have the percentage of clay and so on. The alternative is to, one of the alternatives in sedimentation is to use Bouilloukos method rather than the pipette. Bouilloukos is a device. I don't know if you see me because I only see my screen, but this is the kind of device here. The idea is that you have something which is well calibrated. The density is known, and there is a rule here, and you can measure you put it simply in the column, and you measure the what is given on the rule, and it gives you the quantity of kind of density. It gives you the quantity of soil that you have in the suspension. So yeah, I made photos of this one. You see, it tells you here how many suspension you have in the column of sedimentations in grams per liter, and it's calibrated for given temperature here in Fahrenheit. So the idea is that you can use that always a question of defining the time to make the measurement according to the size of the particle and the temperature. So it's the same principle, it's just a different kind of measure. Regarding the quality of what we can measure with the sedimentation here, it's kind of we had some measurement, and we put in the series, in every series, we put a control sample. And here you have the value of the control sample. This is control that have been certified by the BPA. And so we know that there is a target value here. This target value is calculated on the base of all the participating laboratories. So it's a general mean, and according to the variation that you could have, you have tolerance value. So we know that this is the target value. And our standard should be between the red lines. And so that's what we had recently. You see that there was some of the samples which were a bit lower of the target value. One was really at the limit of the red elements. We checked with repetitions, and we say that we didn't see why there was it was so low. And then the series after, and the fourth series after, you see that we were very close to the target value. So without really changing anything in our procedure. So it means that you have sometimes this kind of effect of variability. So this is on the USDA triangle, the plot of the various the soils that we analyzed, and we saw globally 3 groups according to the level of clay content. We have here a group with 17 of the soil samples that are clearly higher in clay content. We are over 30% of clay. We have an intermediate group here with 8 samples, which are on the loam side. And then we have here another group composed of 2 groups with the lowest clay level, and it seems that there is a kind of a gradient of sand within this group. So regarding particle size distribution, I think that it was rather clear that there were three levels of clay content in the soils that we received and that we studied. Okay, that was for the particle size distribution.
Okay, thank you, Jill. Maybe it's good that I mentioned that indeed you were referring to the samples you have analyzed. So indeed, we have received some couple of months ago some Ukrainian soil samples that we were asked to analyze. So indeed, the results that Gilles is presenting is part of more or less, I think, 40 soil samples that we have analyzed and of which you have now shown the results. Then maybe a question to you. I think this is probably one of the most labor-intensive methods, all the different steps that you have seen. Sometimes people also make use of laser diffraction for performing the analysis. Could you comment on the difference or say something about laser diffraction versus the pipette method?
Yeah, it was one of the debates in the GLOSOLAN too. And the lab here are asking the lab of soil analysis in southern Belgium are also asking whether it should be interesting to use the laser. The problem is that the particles are, according to the Stokes law, should be spheres. And we know that the real particles are not spheres. If you take the clay particles, it's a kind of sheets, small sheets. And so the dimensions are differing according to the dimension you take. So, and the laser counts that. It sends a laser and say, okay, there is particle or there is no particle, and so on. So the principle is not the same. Even if a part of the preparation of the sample is the same, you must remove the binding agents and so on. It's the measurement that is a bit different, and it gives you information about the count of the particles, and the difficulty is that there is no easy correspondence between both methods. most of the references have been gained by the pipette method. And if you know must change and have the laser device, you need to rebuild a new reference system.
Yeah.
And it depends on the context probably.
Yeah.
But
No.
a part of the, I think a part of the procedure is still the same. It's the longest part. It's all the preparation before the measurement.
Yeah.
It's
Yeah.
difficult to discard that.
No. Okay, thank you. Gilles, I think it would be good to have a small break now,
Yeah.
if that's fine with you. Let's say 5 minutes.
Okay.
So we will have a break now for 5 minutes, and then we continue with the cationic exchange capacity.
Okay.
Okay. Gilles, I
Yep.
see you're back. So yeah, I propose to go on with another dimension of what you call the fridge.
Mm.
So please go ahead.
Okay. So cationic exchange capacity is the quantity of cation that the soil can have retain on its surface and exchange with the solution. There is a general statement that say the higher the CEC, the higher the soil fertility. So maybe it's sometimes true. The origin of the cationic exchange capacity is double. First, you have the clay, so the mineral part of the cationic exchange capacity is linked with the clay, and in the clay you have tetrahedral layers and octahedral layers, and in the tetrahedral, the ion which is at the center is the silicium, which is usually a charge of 4 plus, and there may be some replacement that are called isomorphic replacement, and the Se4 plus is replaced, for example, by Al aluminium 3 plus. And so 4 plus, 3 plus, there's a deficit of charge because the surrounding of oxygen doesn't not change. So there is a deficit of charge, and we call that there is a negative charge. And the same in the octahedral layers, the aluminium, which is 3 plus, can be replaced by iron or magnesium, which are 2 plus. And so there is a global deficit of charge, and this is called the permanent negative charges. And so permanent because it only depends on the number of substitution that there has been in the structure. And also, if you look at the structure, you have oxygens at the border, and the oxygen have negative charge, but according to the pH, they can be bound to H plus or not. And these charge, so the dissociation of a hydroxyl component depends on the pH. When the pH is high, it will globally interact in order to attract the proton or to put the protons in the solution. So this kind of charges varies according to the pH. And it's the same for the soil organic matter. They have functional groups which usually have OH that can dissociate. If the pH is acid, that will be OH, which will go in the soil solution. And when the pH is, the reaction is basic, it will be H, which will counteract in the solution. And so the more basic, the more you have negative charges here on the surface of the soil organic matter. And these negative charges are dominant, and it means that the cation can be linked to these charges by different kind of relationships. Some relationships are just attraction of plus and minus charges, and other charges will be sharing the electrons, and sharing the electrons is a more strongly bound relationship than just plus minus binding. There are different kind of, I forgot to put the source of the paper. I will correct it. So there has been a review of, not completely a review, but a study made by Flemish colleagues in order to compare different kind of cationic exchange capacity on different soils. And they made a kind of review of what were the most common, and say that you will find the ammonium acetate cationic exchange capacity, which is the one presented in the SOP from the FAO. But there are also other, such as using BaCl2 and precipitation with sulfate, which is single extraction of BaCl2 and measuring the quantity of Ba in the solution. Others with silver compound, and another one which is more and more widely used is the cobalt-examine method. It's a one that we also made sometimes. That one, the first one, ammonium acetate, is usually buffered at pH 7, so at a neutral pH, while the cobalt-examine is a kind of method that gives you the cation exchange capacity at the pH of the soil, at the true pH of the soil. So the compounds that you put into the exchange does not modify the pH. Here, with the first one, you force the system to be at pH 7. And so they will give different kind of results. One is buffered, and the other one is at the pH of the soil. So we worked with the SOP from FAO, which uses ammonium acetate 1 normal buffered at pH 7. Globally, it is widely used, one of most widely used method for the CEC. There were different kind of version with making solution percolating through the soils, or the one which is mixing and shaking, and the one in the SOP here is by shaking, mixing and shaking. And so the general idea is to put ammonium acetate, and the ammonium will replace the cation that are on the cation exchange capacity complex. They will replace it, and it means that you have in the solution the calcium, the magnesium, the potassium, and the sodium that was on the exchange complex, and you can measure them separately. After, you will try to determine how much ammonium you have put on the exchange complex. And for that, you will have to remove it from the soil and to measure it. So the methods is widely used, but it's known that it overestimates the CEC of acidic soil. So that's why it's because it's buffered to pH 7. The methods also underestimate the CEC for soils which have a high level of carbonate or of gypsum, because when you do that, you are dissolving these compounds when you put them with ammonium acetate. And also caution should be taken for soils which have vermiculite and mica clays, because the ammonium can be fixed more strongly in them, and you cannot measure them anymore. So the general principle is that you treat the soils with the normal ammonium acetate. Then you quantify the cation by atomic absorption or emission spectrometry. And the excess of ammonium is removed by washing with the ethanol. So you saturate the environment with the ammonium. You discard the ammonium which is not fixed by washing with the alcohol. And then you desorb the ammonium by usually distillation and titration with in basic conditions. So regarding the procedure, you weigh 5 grams of soil and you add 30 milliliter of ammonium acetate at pH 7. You shake, then you centrifuge, you filter, and you put your supernatant in a 100 milliliter volumetric flask, and you repeat it. So you make it 3 times. So at the end, you have almost 100 milliliter of supernatant, and you put it at level 100 milliliter. So you had 5 grams of soils in 100 milliliter of extraction solution, and in that extraction solution you have all the cation that you wanted to measure. So that's the various steps here. You have the products, you shake, prefuge, you filter, and then you level at 100 milliliter. And with that you can do the measurement of the cation. Usually you have to make dilutions and so on. So here we use the ICP-OES, and it's just illustration images. Then you must wash the excess of ammonium. So it's the same principle. You put ethanol, you shake, you centrifuge, and you eliminate the ammonium, the ethanol. You use the Nestler reagents in order to see if you completely remove the excess of ammonium. So it's not in the image, but the idea is to not to go too far in the elimination of the excess of ammonium. Usually, we have 3 to 4 washing by the ethanol in our procedure. And then the idea is to remove the adsorbed ammonium from the soil. In the procedure, it is desorption made with NaCl solution, and you just the same. You put the NaCl, you shake, you centrifuge, and you repeat it. And at the end, you have 100 milliliters of NaCl that you will use for the distillation and titration. In our own methods, we use the NaOH and not NaCl, and we just put NaOH, and then after we make distillation and titration. But in this specific study, we stayed in line with the SOP of FAO. So you will make a distillation. So it means that you put vapor, and vapor takes the ammonium away, and it is trapped in a solution of boric acid. And you will titrate after the solution. So this is the operation. So we take 50 milliliters of the extract. We put it in the Buchy distillation chambers. Then we have this trap with the boric acid. And we make the titration here with the HCl until the change of color. So, regarding the results, I put here bars with the cumulated Ca, Mg, K, Na concentration, and usually they are expressed in milli equivalent per 100 grams or centimole charge per kilogram, which is the same unit. You don't need to transform to one into another. So it's in molar units and not in concentration. And the same for the cationic exchange capacity. It's the same unit. Normally, you can evaluate the ratio between the sum of your cation Ca, Mg, K, Na and the cationic exchange capacity, and it's called the saturation ratio. The saturation ratio in base of your soil. Normally, on the CEC, you should have these 4 cations plus the exchangeable acidity. As we are on in carbonated environment, when we are in carbonated environment, with the procedure, you can dissolve calcium, which is not really on the exchange complex, but which is in the minerals, and so you put it in the solution where you will do the measurement, and you will find that you have an oversaturation of the cationic exchange capacity, which is not completely true. So there is a recommendation in the SOP of the FAO, or not produce the result of the calcium when you have carbonated in the samples. If you have dolomite, you could have the same problem, that you overestimate the real quantity of magnesium. So here you will find the sum of the cation, and the line here is the cationic exchange capacity. They are both with the same scale. So it means that if the sum of the base is over the CEC, you have an oversaturation, and usually it's linked to the blue bar. It's the calcium. And indeed, we have here the 39 samples from Ukraine, which present trace of carbonates, and see that with these results, we just can say that the fridge is oversaturated in some places, and at other places there are still room that are occupied by other elements. With this view, you see that calcium is the dominant cation, and then it's magnesium, then it's potassium, and sodium is clearly very low in that proportion, and it's completely usual. So I discarded the calcium in order to see the proportion of magnesium, potassium, and sodium here in the graph. And as you can see, usually sodium is very low in concentration, and most of the difference here are linked to level of magnesium. See that we have here the first soils that seems very poor in terms of some of the four. Then you have a series here for which the level is a bit higher. Again, here poor soils, here intermediate, and here say in between these two. So we had four level, one here, one here, one here, and one here, according to the samples. An interesting indicator too in this is the ratio of potassium to magnesium. There can be interactions between these two when especially for some crops or the grassland. If there is too much of one, the uptake of the other one is not good. So if you have too much magnesium, you will have problem of deficiency in potassium. And if you have too much potassium, you might have deficiency in magnesium. And so the blue line here is the ratio of potassium to magnesium. And see that there are a strong variation. Here you have levels which are very high compared to the other one, which are much lower. And here you have something which is more intermediate. The exact value for telling that there might be problem is a bit tricky too. Sometimes you find 0.2, 0.3. What we might suspect here is that maybe for these which are below this dashed line here, maybe you could have problems of well, not enough potassium and compared to magnesium, and maybe for that you would have the too much potassium compared to magnesium. So it's maybe we have potential problems of fertility that need to be confirmed for these soils. Another point with the cationic exchange capacity, we know that it is due to mineral and so mineral is the clay content and also organic matter. Yeah, there's a wrong title here. It's organic matter content. We made a modelization of the CEC according to the clay content and the talc content. And this is the model value, this is the observed value, and see that there is a clear relationship. It's also a kind of validation of the methods that a quality control of the data. If you have so clear relationships, it means that the three parameters are quite well analyzed. And so, yeah, if you have to choose about properties and you don't want to make a cationic exchange capacity, you could maybe have a prediction based on the organic matter and the clay if needed. So that was the part related to cationic exchange capacity. I don't know if there are questions about that.
Yeah, thank you, Gilles. I think one of the questions was, if I understood right, yeah, and if you go to the previous graph, yeah, this one. So the fact that the stacked bars with the calcium are higher than the
Yeah.
line of the CC means it's oversaturation.
Yeah.
So basically, you mentioned that it is due because we have like a carbonated environment. So this, in other words, as I think you mentioned previously, basically this method is, yeah, not really applicable for these kind of soils. So the question is there any limit value from which you would say, okay, with this carbon content or with this calcium content, it is difficult to use this method and maybe another method should be preferred? Or is this difficult?
It's difficult, yeah. I think the evaluation of the CEC is correct. You see, it's just that it's the quantity of elements that are on the CEC, which is not well estimated, because you are overestimating the quantity of calcium or magnesium. But here it's linked to calcium. So it means that the CEC is correctly measured, probably, but if you want to make estimations about the quantity of elements that you can store, or the quantity of acidity that might be on it, you may be a bit wrong.
Okay. And how to interpret the saturation, the percentage of saturation? So this ratio, does it has a link with fertility or how to make this interpretation?
Yeah, there is a link between acidity level and base saturation. Usually, you try. It's the other day I told, is it better to have a small fridge which is well furnished, or a big fridge which is empty? And this base saturation is a kind of indicator of your fridge is empty or not empty.
Mhm.
And so the base saturation, you try to maintain it at least at 80% of the size of the fridge. And if you go under, you say, okay, probably we might correct by adding more furniture in it.
Yes. No. Okay, that's clear. And another point, I think in one of your previous presentations, you also mentioned that there is sometimes some kind of ratios between calcium and magnesium in the soils within certain limits. Could
Yeah.
you consider this as well to check if, for example, here you have a lot of calcium, that it is too much as compared to magnesium, for instance, and potassium? Is this also a way how to look at it?
Yeah. Sure, there are ratios of calcium to magnesium and calcium to potassium. Here, I don't know if we can really take it into account, this calcium, as it is
Yes.
oversaturated. You see, as we took more than is really in the soil solution. That's the idea.
Yeah.
It's difficult to say that you will calculate will be relevant or not.
Yeah, it was more meant as a control check. If, for example, you see that calcium to magnesium is more than a certain ratio, you might expect that calcium has dissolved. This question was more related to that. If there is some kind of an indication, if calcium to magnesium is higher than that, maybe you have had some dissolution of carbonated environment. Or is that not so
No.
straightforward?
I'm not sure. No, there is an ideal, but also it's a vision that is not shared by everyone. But there's an old concept that said that there is an ideal balance of Ca, Mg, and K on the CEC, and you should try to maintain it as close as possible as that. And it is 60% of calcium, don't remember exactly, but 12% of or 20 of magnesium and 12 of potassium, something like that. And you should try to maintain it. But I know that there are other agronomists that says, though that's bullshit. It's not like that you should consider. But
No.
the best is to have a reference system in which you had made some experiments and you know that given that result, you will face some problems for that crops and so on. But when you don't have these reference, you must work with these rather simple concepts.
Yeah. Yeah. Okay, maybe. And then just a last question out of curiosity. You said in your method, as compared to the FAO method, you use sodium hydroxide instead of sodium chloride. Has it to do with possible losses of ammonium that you have an alkaline pH extraction, or why do you have sodium hydroxide instead of sodium chloride?
Yeah, I think it's because at the end you make you when you are making your distillation, you need when you do it for the total nitrogen, for example, you add NaOH in order to volatilize the ammonium. And here, I think it's something like that. It helps to remove the ammonium from the soils. But after you need to take care to avoid the too much volatilization of
Yeah.
ammonium. Indeed, yeah.
Yeah. No? Okay, I don't see any more question, Gilles, on this topic. So I propose we continue
Yeah.
with
It was just some slides in order to go further in the integration of data based on what we had as a measurement, and I go back with the PCA analysis here with all the parameters that were used. And you can see that now they are going into different directions. You have a first dimension where you go, you will find the clay, the sum of the base, and at the opposite you will have the sand, and we don't know exactly why, the iron extracted by DTPA. So this is one thing is at the on the first dimension, and if you look at the second dimension, you have manganese, copper, iron extracted by the DTPA, and at the other side you have more pH, calcium carbonate, and so on. And so if we plot the samples, just looking on the first dimension, we could say, okay, maybe we should make one group here, which should be the more sandy, the less clayey soils, but they also have a lot of iron. And at the other side, you probably have here one group which should be richer in calcium, magnesium, silt, more loamy. Here, the more clayey and group. So you can say, okay, maybe I make 4 groups and I still have some points here which are maybe close to that one, but I don't know exactly where I will put them.
um, uh, Gilles,
Yeah.
sorry to interrupt you. If you go to the previous, could you briefly explain how you built the figure on the left and what the arrows represent and why they are pointing to a certain direction?
Okay. So that's multivariate analysis, the PCA principal component analysis. It's a way of looking at all the variable, what they share as a variation. For example, if there are 2 variables are well correlated, they will go in the same direction. And the statistical tools do that for every parameter, and he builds new variable based on that. And the first dimension will be a kind of new variable, which is correlated to the other one at certain with a certain level, and the more it is correlated, the longer the arrow is. For example, in the first direction here, it's here. It is the first new variable that the system has built, and the second one is there. And he makes as many new variable that there is variable. So it's a bit complicated to to explain like that, but it's a way of reducing the information by giving emphasis on the correlation. It's a way of showing that variables are correlated. These are grouped all together. It means that they have strong correlation. These have strong correlation, and these too. But it's only a partial vision of the system. So here we say that if we look at the variation of all the parameters, I don't remember exactly how much they are, but let's say 20. The 20 parameters, as they all have variance. And if you look at this image, we see that we have here 38.3 and here 20.6. If you sum both, you are almost at 60%. So it means that 60% of the variation of all the variable is represented in this image, and it's missing 40%. And the variables that are not well explained are here at the center, such as the ammonium and the zinc DTPA. They are not well correlated with these variables. And so here we just have a look at the first dimension is like that. And we see that there is elements that push, all these push to the right. And so it means that the high value of this parameter will be in that part of the graph, and the low value will be in that part. And at the opposite, the high value of sand and iron DTPA will be here, and the low value will be there. And so that's when you plot the samples, they are located by the influence of all these variables. And then you have a second dimension. If you look in that direction, you see that here to the upper part, you have a pressure of iron, manganese, copper, phosphorus. And at the lower part, you have the pH, calcium, carbonates, and so on. So you will find here the more basic point, and here the less basic point. Here you will find the higher content in manganese and iron DTPA, and here you will find the lowest. So it's a combination of all these variables that are plotted here. And here, the larger the point, the better they are explained by this graph. And the smallest, yeah, you see here, you have some which are very small. That means that they are not very influent in the process, and they should be explained in other dimension. Don't know if it.
Yeah, thank you, Gilles. I think it makes, for example, if we look at point 20 on the figure on the right,
yeah.
So this means it had a relatively high sand content, if I'm correct then, because this is on the axis of the high sand content. Am I correct?
Yeah.
And a relative low, for example, TOC content, because the TOC is on the on the other side. Is this how we should read it as well, or you can?
Yeah, we should check individually, but that's the idea. Yeah.
Okay.
This one can be there because it is sandy and few organic, or it can be the influence of this one. Maybe it is very poor in Mg and K, but things are not excluding. Yeah.
No. But here it's a question of trying to group the different soils. That's okay. Thank you, Gilles.
Here it's trying to say, okay, what group I can do, and with this group, can I have appropriate solutions to, if I can say, okay, for these groups, I have this kind of fertility problems, it will be easier to manage. That was basically the idea. And so what I did after is to make a classification, not only based on the visual expression that I had on this graph, but by using all the dimensions. And I asked him to stop here. It's the default value. He stopped after by making 3 groups. And I put the 3 groups there. So if you take into consideration all the variables, you will say, okay, this is a group, this is a group, this is a third group. Same colors. If you had wanted to cut at a higher distance here, it means that you probably would have made here, if you cut here, you have made another group, which is that one, and 22, 1 and 2, and that one, you see. If you had cut here, you would have made a difference between this and the other one. So yeah, it's a lot of details here, but by default, this is what I received as information. When you just make a separation, you have 3 groups, and I just try to see, okay, but now that I have my 3 groups, I try to characterize what makes their differences. For example, here, you look at the clay content of your 3 groups, and you can say, okay, first group is low clay, second middle clay, and the third high clay content. Then I look at the total organic carbon. I can say that the first group is low in clay, but also low in organic matter. And these two are not clearly different. If I look at the pH, again, these two are not so different, except that maybe the group 3 is more variable, and see that the pH of the first group is low. So in this group, first group, low clay, low OM, low pH, so probably low fertility. And if we look at the nitrate, we look at the phosphorus, and we look at the potassium, we see that, to the exception of phosphorus, the first group here is always the lowest in terms of fertility. Second group is a bit intermediate, but he has low potassium. And this group here is highest clay, variable pH, but the highest potassium. So probably the third group is the most fertile one, and maybe does not need special care. While if you have to put your efforts into improving one group, you should focus on that one. That was the main idea of this exercise. And I think it's done.
Okay, thank you, Gilles. I think it's really interesting to also show how you can deal and what you can do with the data. Maybe I'm looking as well a little bit to you, Nathan, because if I remember well, the samples we received, I think they come from, 5 or maybe 6 locations. So it would be interesting to check. And maybe if you go 2 slides back, Gilles, on this. Wacht, no, one more. Well, yeah, this one. I think if you would go one level down, you would on the figure on the left, you would have like 1, 2, 3, 4, let's say 5 groups, more or less.
1, 2, 3, 4, 5.
Yeah. And I'm wondering if later on we we can check the data. This would correspond also to the 5 places of the samples that we will receive, just to check indeed it's a good way of controlling. But maybe Nathan, you can comment on that.
Yeah, I was going to pop open the data and look because I assumed they're just different geographical regions, but I was too tired.
Yeah.
But they're probably just different soil types from different regions, from different oblasts would be my thoughts if they look at them more closely.
Yeah, for some it looks like the sandy maybe more soils on sediments or something like that, and the other one clayey and so on, maybe chernozem. So don't know exactly. Yeah, it should be interesting to go further, but
yeah. But I think that's part of the plan. We have now the data to go a little bit more in depth on the data we have, and to also make, I mean, just what you did. So it's already a good introduction, Jill. What you show here as tools that you can have to combine samples to check for variability, how much this is explained. So I'm looking at the audience if there are still some questions on or remarks. I think what I learned especially is the concept of the fridge. Thank you, Jill, for that. So I think
sometimes it's a basket, but we use
Jill,
a fridge. Yeah.
Jill, I know you're doing quite a bit of comparison here between the different soil types and the ones already analyzed, but because I'm not as familiar with the agricultural parameters, I suspect there are guidelines for appropriate ranges, like there is for pH or nutrient parameters. And I imagine there are a lot of different places that give guidelines. I suspect, does the FAO have such guidelines for different levels, or where's the best place to look to see if your soils are within a healthy range, I guess, for these fertility measurements?
I'm not sure there are thresholds. I think that Christophe mentioned, I think you mentioned the new publication from about the soil status of the in Europe. I think I just had a quick look. I wonder if they suggest a threshold for phosphorus, but no. It's not so easy. It's not so easy.
I think they did, or they tried to come up. So I think, but it was more like phosphorus excess and phosphorus deficiency, for example.
Yeah.
And but they give number like if the phosphorus excess is lower than 20 milligram per kilogram,
20.
then you have a phosphorus deficiency. If it's higher than 50 milligram per kilogram, then you would have a phosphorus excess.
Mm-hmm.
So, okay. but these are just, I mean, very general. But maybe if you would dig deeper in those data, you can find maybe references. Yeah.
Because I mean, I come from the contaminated sites side of things, where the numerical standards are quite specific, and if you're over that, then actions have to be made. But I suspect with this sort of stuff, it depends on the soil type and what you're trying to grow and the climate. I bet there's more factors as far as agricultural soil is concerned.
Yeah, but as I told the other day, I found a study that was made on assessment of farms in Ukraine, and they were tables with the evaluation of this is high, this is low, and so on. So there must be a standard assessment scheme for Ukrainian soil. It would be interesting to have it to know how where they put the threshold for this given area, because there was a lot of experiments, a lot of research done so far there, and so I'm sure that the threshold are adapted to the situation. But yeah, the difficulty for us is to get access to this information.
Yeah. Yeah, that's correct. I just put the link to this report that can be downloaded of the state soils of Europe in the chat. So it's a report that just has been published, I think, 22 of October, so very recently, with some very interesting data on Europe. Also, some Ukrainian soil data are discussed. I think it's a very readable document, which gives you also a very good overview of all the different things we have been discussing as well. So I think I would really recommend you to go through it. It's not a very large and it's very comprehensively written. Unfortunately, it is in English only available. But there are also some nice graphs and also some indicators, as Gilles was suggesting, like, okay, what are certain limits that are used and so forth. So I just put it for you as information in the chat, but I think it's a very worthwhile looking document. Okay, I don't see any more questions yet. I think it was a lot of things we discussed today, Gilles, and it will be a lot of more to do it in practice. So I think all the things that you show will also be performed in your lab, all these kind of parameters. So yeah, I think having said that, I just remind all of you that the next session will be on Monday at 10 o'clock Brussels time. So this means 11 o'clock your time. It will be the rescheduled session on radiochemistry. So it's a general session on how to deal with radioactivity. So that's on the Monday morning, and we canceled the session of the afternoon, but I guess that Anna has probably updated you by now with the new timings. So it's only that session, all the rest remains the same. So for next week, we will dive deeper into some of the analytics as well. So also with that, I think considering it's Friday afternoon, I think it's maybe good, Gilles, that we don't push it too far. Sorry, Thursday. Oh, sorry, I'm Thursday afternoon. Sorry, for me it feels like Friday.
Yeah,
no, it's Thursday afternoon. So, but we leave it here, and then I wish you all a good evening, and then we see each other on Monday at 11 o'clock your time. Thank you, Gilles, one more time for your presentation.
Thank you. It was a pleasure.